Welcome. Today we're going to be talking about scaling large language models on Google Cloud with Spotify. I'm Brittany Rockwell. I'm a product manager at Google Cloud. I focus on AI inference. Specifically, I do a lot of work on our open source projects that land TPUs in open source in your favorite inference engines. I'm joined by Shireen Kheradpey, staff machine learning engineer at Spotify, who will go over how Spotify is invoking all these important composable parts in inference to power some of their most important production workloads. So first, I'll go over how Google thinks about inference, just in general, kick us off, talk about our new chip, some of the software developments that we're making, and then with the new Gemma launch, how this all intertwines with model redesign. Then Shireen will go over Spotify's AI platform and specifically illustrate how Spotify is using GPUs and TPUs to power some of their most important workloads in recommender systems and safety. And then I'll close this all off and we'll cover how you can get started on TPUs. Okay, so large language models and how to run them on TPUs. So as you all know, workload complexity has just exploded significantly over the last few years, not just in how large models or how much larger models are getting, but just in how systems are extremely complex now and how they're interacting with one another. We're also adding different types of modalities like video, audio, and text that have to be simultaneously processed at one time. This is all driving longer and longer context. It's driving harder demands or larger demands on HBM. And it makes inference a really, really hard but interesting problem to solve. And so what's required is a highly efficient system across hardware, software, all the way to models, how you design and architect a model, not only open weight models, but also your closed weight custom models, how you actually design them to run really efficiently on the hardware that you need to serve on. It becomes a really fun problem to solve. So our vision on our team is to make it effortless for any customer to serve their models on TPUs and to deliver industry-leading price performance and a state-of-the-art developer experience for large-scale production serving on TPUs. So let's start with hardware and how TPUs are built to meet this inference moment. So TPUs have actually been around for a very long time. Some of you might not know that, but the first TPU v1 chip was announced or was released back in 2015. And so there's been tons of innovative or iterations that have happened on this chip just to meet how inference has changed over time from, let's say, over 10 years ago to today with the new, or yesterday with the new 8T and 8I chips that were just announced. Because of this long lineage of innovation, we've accumulated a wide array of different AI innovators with different maturity levels from some of the most sophisticated AI labs and academic institutions to large-scale enterprises that have to use different hardware just based on the massive demands of their global applications that have to be served. So with 8T and 8I, we've really come out with these two different chips to serve an end-to-end life cycle of a model, right? So starting from pre-training with 8T, massive scale, training workloads, and then passing that same model off to inference for 8I that has to run extremely efficiently at scale. And then, of course, back for a reinforcement training loop for post-training as part of this cohesive system. So for 8I, for instance, we've reduced the number of hops that you have to make due to the topology changes to 7. We've increased the total SRAM to 384 megabytes to support larger and larger KV cache for low latency serving. Because of the board fly topology, we've also reduced latency significantly by 2x when compared to our previous generation. And then we've also improved performance per dollar by 80% when compared to V7X, so our previous Ironwood chip. So all this is really exciting and shows that we're designing chips at the hardware level to support your most demanding inference workloads. So now quickly moving to software. So we focus on highly performant composable parts in open source to make TPUs go really, really fast. And and in a cost-effective way. So all the way from orchestration to the inference engines, all the way down to the hardware, we try to land as much as we can in open source so that you can build your own stacks and have the flexibility to do that if you need to, while also providing well-lit paths where you don't have to figure out all the nitty-gritty parts. What we found is that the open source inference engines like vLLM and SGLang have become really the bedrock of the inference industry. What this means is that foundation model builders that are releasing open weights, like Google, for instance, like with the new Gemma model, they can land their open weight models in vLLM, let's say, on day 0, and make it available to users right out of the gate so that they can start actually testing it for quality. So it becomes a really important distribution channel for them. But these engines have also moved to supporting different hardware backends across GPUs, CPUs, and TPUs, and many, many others, actually, while still retaining the same API interface without having to kind of go through the toil of switching different hardware backends that you historically had to do previously. And then because of this, there's this massive community traction that we're seeing from both academia, AI labs, and enterprises, where everybody's contributing code to these open source projects. So it creates this really important flywheel. So for that reason, the most popular inference engines in SGLang and vLLM, our Google-led vLLM TPU project was just announced with a completely re-architected system in October 2025. And then shortly after, SGLang JAX was announced that uses a lot of the same composable parts that we wrote. And we're really, really excited to support these two projects, but also just any project that comes along. So with this, you can drive better perf per dollar using TPUs, but you can also improve obtainability, as Shireen will kind of cover, is that you're just increasing your total hardware pool because it's, there's capacity constraints now. And then third, because we've integrated directly into these open source inference engines, there's near zero developer friction in terms of it's the same configurations, or it's the same user experience that you're already having for your developers. And then what is deployed in production stays relatively the same because we've embedded directly into these engines. So very excited about this. So if you want to get started, we've linked reproducible recipes for our most recent Ironwood chip across Qwen 3 coder and Qwen 332B if you want a really performant example using vLLM across different data distributions, so from prefill heavy to decode heavy. Okay, so models, super cool. So TPUs support a broad set of open source models, but we're going to dive into Gemma because it was just announced Gemma 4 was just announced a couple weeks ago. So Gemma 4 is awesome because it was co-designed for Google TPUs. So it was trained on TPUs, but it's really designed to be deployed on many different types of hardware backends, from personal devices to server-side, data center hardware. And what's really cool about the Gemma 4 models is they're quite small, but they're mighty. And so they outrank models that are 10x their size in terms of quality and human evals. This is for the 31B and the 26B MOE. Also, for the first time ever, Gemma 4 was announced with an Apache 2.0 license, unlike previous generations. So people are really excited to just basically be able to hack and do whatever they want with it, which is awesome. It's our first reasoning model that Google has announced openly. And it's designed for agentic and multimodal workloads. And again, it's trained on TPUs, but designed to be deployed on various different hardware backends. So this is a great example of going from hardware, software, all the way to model co-design, and how that full stack is just how you get the best out of the hardware that you're basically purchasing. So from our 8i to 8t, we've designed these specifically to kind of meet the moment for inference and how these complex workloads are changing over time. And then for software, we're deeply committed to open source. And so we're seeing an increase not only in the community and how the community is adopting TPUs, but as Google, we're also very committed to growing this ecosystem overall to make it as portable and easy for you to start using different hardware backends. And then for Gemma 4, not only are we really indexing on Gemma 4, but we're also creating partnerships with other open weight labs, for instance, to make sure that we're getting the word out on how we actually design architectures for both TPUs, GPUs, and any hardware that you need. So now I'm really excited. I'm going to hand it over to Shireen, who will go over how Spotify is using all of these different composable parts in production to make their workloads go brr.
Hey everyone, I'm Shireen Kheradpey, and I'm a staff machine learning engineer at Spotify. And I'm here to shed some light on how the building blocks that Brittany mentioned come together to form an inference stack that helps productionize AI workloads at Spotify. So a little bit about where I sit at Spotify. I'm on the machine learning platform team. So our role is to build and operate the infrastructure that powers the entire ML lifecycle, from training and fine-tuning ML and AI models through to performing inference. So we figure out how AI and ML models are served, what infrastructure they run on, and how they scale to our 700 million users and over our entire catalog. So product teams and modeling teams can focus on building experiences and not worry about the complexities of how to deliver these experiences to all of our users. As platform maintainers, we've had a front row seat to the progression from classical ML to modern AI systems. With classical ML, the pace of change was much slower, so frameworks and infra shifts happened over years. TensorFlow was the dominant framework around 2019, and then in more recent years, PyTorch grew in popularity, but this happened over the span of years, so it gave infra a chance to keep up. But with AI, the frequency of change is much faster. And what used to happen in years now changes in months. So new model families, new inference engines, new hardware options are constantly being delivered. But the commonality between both AI and ML models is their trajectory towards accelerator and compute demand. And again, part of our AI and ML platform team is to make sure that product innovation is never blocked by the lack of compute. Since exponentially reserving GPUs isn't sustainable, both from a cost standpoint, also from a supply standpoint, our infra team strives to maximize the usage of the compute we have and also find alternatives to relieve some of this GPU pressure. So today we maximize GPU usage across our fleet through a shared GPU pool. So our recommendations, safety, search, and other workloads all draw from the same capacity. And this model lets us better use our accelerators because of the dynamic nature of these different services. One workload might spike while another tapers off. So this shared capacity better lets us utilize our accelerators rather than just statically assigning accelerators to a specific workload. To further alleviate GPU pressure, we're moving towards an accelerator strategy that includes both GPUs and TPUs as part of this shared pool. So that means understanding workload fit, which workloads run the best where can we meet the same SLOs, and furthermore, where can we achieve the best accelerator economics. Before we deep dive into some concrete use cases, I want to highlight that innovation happens both on the modeling side as well as on the infra side. On the product and modeling side, new AI features are launching and existing features are being constantly iterated on through model upgrades and tuning, often pushing the limits of our inference stack. So as we build out our inference stack, we're constantly evaluating every infra building block from the perspective of, does this bit of infra fit our immediate needs? And also, will it evolve as our needs and use cases evolve? So our platform team is here to keep the product need and infrastructure aligned so that product teams can adopt the latest models and innovations without worrying about their feature being able to productionize across our users and Spotify load. And that brings me to a couple of use cases that I'm going to deep dive into. The first one is AI recommendations at Spotify. So you might be familiar with some of our more AI-forward features at Spotify, including AI playlisting and AI DJ. AI playlisting is a feature where users describe in natural language a vibe, a mood, a genre of music they're seeking, and Spotify generates a playlist on demand to fit that user prompt. Under the hood, LLMs were mostly translators turning this free-form user prompt into structured signals that our recommendation systems could use. And that evolved into a more interactive experience like our AI DJ, where users can talk to our DJX, and DJX, with the help of LLMs, acknowledges those user interactions and introduces the music recommendations that are surfaced to our users. So we only have one human DJX, so to make this recommendation entry point scale to our millions of users, we leaned on open-weight LLM models hosted and deployed through vLLM on GKE to scale to our Spotify user base. Scaling AI DJ demands a fleet of GPUs and is just one of the many AI workloads that we host in production at Spotify. So we on the infrastructure team are constantly searching for ways to relieve some of that GPU pressure. And this is what motivated us to start evaluating TPUs as a hardware alternative to augment our GPUs. And we found that these text workloads could meet latency targets, and in some LLM interactions for AI DJ, TPUs yielded a potential cost savings of around 30% compared to hosting on GPUs. And because we were using vLLM already to host these LLMs, we could evaluate this new hardware path with just 2 lines of code changes. So up until this point, LLMs were used mostly at the edges of our experience, so understanding user prompts and orchestrating that routing to different ML algorithms. As application teams continued to test out new ways to enrich recommendations, the role of LLMs were pushed beyond natural language. So LLMs became actively involved in recommendation algorithms themselves through candidate generation or creating a pool of next tracks and podcasts that we should surface to a user, and also the scoring and ranking of those candidates to help applications decide the best content to serve up to the users. So this pushed LLMs deeper into the stack and multiplied the load sent to these LLMs. And we take context about a user's past listening activities and use LLMs to produce hundreds of content candidates at a time, and that propagates to hundreds of candidates to score, multiplied against our millions of users. So again, at this Spotify scale, it puts intense accelerator pressure and demand on our infrastructure. The easy answer would be to throw more accelerators at the problem, but 1, GPUs are a scarce resource, so it's not always an option, and 2, our infrastructure teams are constantly looking for ways to optimize our infrastructure and minimize our accelerator footprint. So again, here we evaluate candidate generation, candidate scoring on TPUs. Previously, our AI playlistic and AI DJ use cases were text in, text out interactions, but as we pushed LLMs deeper into the stack, it required us to interact with LLMs in a different way, and because of this, it gave rise to the need to introduce SGLang into our serving stack. But again, as Brittany mentioned, SGLang has both a GPU inference engine and also an SGLang JAX implementation, so that made it really easy to consider TPUs as well as GPUs for these scoring workloads. And we together worked with Google Professional Services to close any gaps and really optimize parity between hosting this large inference workload on both GPUs and TPUs. So at this point, we've introduced new accelerators, new inference engines, and into our LLM inference stack, and therefore more complexity. But why do we do this when we're constantly hearing how powerful API-based models are and how the cost per token for these API-based models are constantly on the decrease? So we do have use cases that start off on these API-based models like Gemini and OpenAI, but as quick ways to get a prototype out and in front of users. But after that initial launch, we're betting on open weight models to continuously improve, as we see with the Gemma 4 launch on top of Gemma 3, and also betting on being able to fine-tune these models on our own Spotify in-house data to continuously improve the quality and produce high-quality content surfaced to our users. So at the same time, we're also betting on the ability to tame the trajectory of our accelerator footprint through different knobs that Google Cloud and OSS communities and infrastructure that we can build on our own. And we've actually seen that raw accelerator footprint needed to serve workloads significantly decrease over years of vLLM iterations. And from a cost perspective, there's both cost efficiencies as well as performance efficiencies gained through also considering alternative hardware types like TPUs. So evaluating TPUs, again, heading in that direction of creating that shared GPU and TPU pool is just a small part of trying to bend the curve to taming our accelerator footprint. So the story is, yes, growth as we're launching new application features and enriching existing features, but it's also growth followed by efficiency as we build our stack out of these different building blocks, OSS building blocks and GCP building blocks. Shifting to our second use case or case study, safety. So safety is embedded throughout the entire Spotify app, and it becomes especially important anywhere we handle user input. For example, when we generate search autocompletes, we want every surfaced query to be safe by Spotify's definition. And when users interact with our DJX, we need both the user request as well as the DJ's response to align with Spotify's brand standards and safety standards. So when you combine this always-on safety coverage across our app, support for our hundreds of millions of users globally, and aggressive latency targets, oftentimes under 40 milliseconds, it creates another large-scale inference load with a significant accelerator demand. Because we were already using vLLM, we could, again, evaluate this workload on TPUs with minimal friction. And what we found here was that in this case, TPUs yielded 40% potential cost savings. And that reinforces that broader strategy of moving towards that shared accelerator pool with GPUs and TPUs alongside of each other. It's not just about adding capacity to handle these new applications that we're scaling, but also about being strategic about what workloads have a higher affinity for better accelerator economics. So in this use case, it's a prefill heavy text workload, and it proved to be a strong candidate for TPU efficiency. Again, the role of LLMs in safety expanded beyond these simple text classifications. Flagging violative content through our platform used to be done through collaborative filtering, relying on user affinity for violative content to lead us to new violative content. But with LLM's multimodal capabilities, we can understand our own catalog better and flag content without the reliance on user behaviors. But this comes at the cost of introducing a higher accelerator and a higher infrastructure footprint to handle the multimodality of our catalog. We have images, we have audio, we have videos, and also handling the billions of media files that make up that catalog. LLMs also made advancements in the multilingual space, which allowed us to expand this English text-based workloads that we had talked about previously and better cater towards our multilingual global Spotify audience. So to better understand our image catalog, our product teams evaluated visual understanding models like the Gemma family, which we then fine-tuned on Spotify data. The product and modeling team workflow involves evaluating different model families, different model sizes, fine-tuning these models, then repeating it all over again because, again, the pace of AI moves very fast, and Gemma 4 launched very recently, and early benchmarks show quality improvements. In this case, we saw a 2.6x improvement on distinguishing high-severity level content. So values that we're seeing, or similar to values that we're seeing with, I think, Gemma 3 12B models were now being exhibited with smaller Gemma 4 model sizes. So we want to leave these modeling teams to focus on optimizing the quality of these models while we focus on the infrastructure side of things. How are we going to host this model, and how will we scale it over our entire catalog? And this is where the different knobs available through OSS libraries and Google Cloud give us options on how exactly we want to productionize this workload. So again, vLLM offers us an easy way to transition between different model families and different model versions. They often have, again, day zero support for these different model version upgrades, so we're able to upgrade quickly and seamlessly. And also, Google Cloud offers us different knobs of how we want to provision these accelerators, because to go over just the image catalog of 4 billion images, this would actually take 2 years of GPU time. So we use things like dynamic workload scheduler, spot instances, and future reservations to tune that workload to run as efficiently as possible and cost effectively as possible for these large-scale backfills. Our final example is multilingual safety at Spotify's global scale. So as we evaluated model families across different language coverage, again, the Gemma 3 family emerged as a strong fit. Based on that analysis, we launched on a fine-tuned Gemma 3 4B model to support to support 70+ different languages. During benchmarking, that workload also showed roughly around 58 potential cost savings on TPUs over GPUs. But again, another example of how quickly AI moves. While our Gemma 3 rollout was in progress, Gemma 4 launched, and some early highlights from analyzing Gemma 4 E4B in particular, this improved hate speech detection by around 2x, and we had 28% fewer false positives that we get for free through upgrading from Gemma 3 to Gemma 4. So you can really see the impact of continuously iterating and increasing the intelligence of our systems through these model upgrades, and betting that our infrastructure footprint will stay the same, or we have enough knobs to bend back the infrastructure and accelerator footprint. And because Gemma 4 was co-designed on TPUs, like Brittany mentioned, we're also optimistic about further increasing the performance per dollar gains as inference engines like vLLM optimize for the new Gemma 4 model architectures. So the takeaway here is that when the building blocks of your inference stack support seamless model upgrades and have hardware flexibility, you can continuously improve your user experience while keeping infrastructure growth efficient and sustainable. To sum it all up, LLMs moved deeper into our recommendation systems, while safety expanded from text moderation into multilingual catalog scale multimodal workloads. So as those responsibilities of these LLMs grew, so did our infrastructure demand. And our response on the platform team was that Platform alongside would expand our inference stack with frameworks like SGLang alongside vLLM to support these new workload shapes, while also analyzing TPUs to complement our GPU fleet. And because these popular frameworks like SGLang and vLLM span multiple hardware backends, we can control exactly what workloads get scheduled on each accelerator to further optimize for cost and performance. And this allows us to create a resilient platform with knobs to continuously optimize for the best possible accelerator economics. So at Spotify scale, it requires multiple building blocks to construct our inference platform. As workloads evolve across more services and introduce more models and more modalities, we need a platform that can adjust just as quickly. And Google Cloud gives us a strong foundation for that. We have Gemini and these API-based models to prototype fast, open models like the Gemma family that we can fine-tune on our own data, GKE to scale to our global audience and customer base, and accelerator optionality on these popular OSF frameworks to relieve some of that accelerator pressure and yield some cost optimizations and efficiencies. And as a result, the result is that Spotify can keep innovating with AI and deliver the best possible experience to our users. Thank you.
Thanks so much. That was awesome. Thanks, Shireen. Okay, so I'll quickly close this off. So just to recap, we just heard like an amazing illustrative story of like how Spotify is using both GPUs and TPUs in their production workloads to serve their most important applications to their end users. This is really driven by hardware, software, and model design. First one being, what's next for us is essentially just making sure that these open weight models run amazingly well and cost effectively on our 8i and 8t chips that are coming out at the end of the year and in Q1 of next year. And then, of course, our big focus is still pushing the boundary on supporting more modalities and longer context on the new state-of-the-art models. And then fast forward, we want to still continue to invest in co-design efforts with with our customers when they're training their models, their foundation models, and if they're releasing them as open weights or closed source models, just making sure that we're getting the best out of both TPUs and any hardware backend that they use in their fleet. So if you want to get started, we've listed off a couple different projects that are really important as part of our open, we'll share this too. You can join us on GitHub. The vLLM link above is the general vLLM project. Then vLLM TPU specifically is a sub repo, and then LMD is just a collection of really high performant open source composable parts that make up a whole inference stack from end to end. And then SGLang JAX is also an important partner of ours. And then of course, if you want to get started with Gemma 4, we have a demo notebook for our Trillium chips and our Ironwood chips. So thank you very much. Yeah, if you have questions, please go ahead. Thanks.